representing enthalpy. In case you're a little confused with enthalpy, please look at the two previous videos that I've created regarding this concept of thermochemistry. First one is the thermochemistry intro, and the second one is the specific heat capacity. I highly recommend you watch those before you continue with this video. Enthalpy here is delta H. We go quite in detail with those two videos regarding the relationship and association of delta H and Q, the heat gained or lost, so please watch that. In this video, we're going to look at delta H being represented in 4 different ways. The first model here we're going to look at is the thermochemical equation. And after we create our balanced chemical equation, we need to implement this delta H. We're going to include it in the balanced chemical equation to become a thermochemical equation. Let's start off with a question. Let's say the question asks to write the thermochem equation Let's say this happens exothermically, so it releases energy. When 2 moles of butane burn in excess of oxygen, and the molar enthalpy is negative 2,871 kilojoules per mole. It's quite obvious we have to start off with a balanced chemical equation, so let's start with that. We're going to first start off with butane reacting with oxygen. Butane is C4H10, again because but stands for 4. It's a prefix of 4 for organic chemistry. So our formula for organic chemistry is 2n plus 2, so you just do 2 times 4, right, from that but over here. You just add it with 2, just gives you 10, so our hydrogen was a 10. So C4H10 plus oxygen yields what? Well, it's quite obvious that this is exothermic, so it's going to release energy, and it's being burned, so that's another hint that this is going to be combustion. And of course, combustion requires oxygen, so it's going to be producing CO2 and H2O. Don't forget our states. Again, with butane, not many carbons here, so it's going to be gaseous. Oxygen, obviously gaseous. CO2, gaseous. And H2O, gaseous. And it makes sense that it's exothermic because it's going to release heat and light, but it's also going to be producing these products as well. In case you're kind of confused with this structure of butane and how this formula is here, you probably haven't learned about organic chemistry yet. I'll make videos on that shortly. But if you haven't learned about that yet, just try to follow along in this video as best as you can. Alright, we need to figure out how are we going to implement delta H into this balanced chemical equation so that we can create our thermochemical equation. Well, first, it's not exactly balanced yet, so can you please pause the video, try to balance it out, and then I'll show you the answer with the coefficients there. Is 2 in front of there, 13 in front of there, 8 in front of there, and 10 in front of here. Where are we going to add our delta H? We still haven't found it yet. Why? Because this molar enthalpy here is not this enthalpy change. This molar enthalpy is only being related to this butane. That's why it says per mole. For every mole of butane, it's going to be releasing this much energy. So how do I find my delta H? There's a specific formula that you can use. Okay, we're only looking at combustion right now. Our delta H, again, is unknown. What is the number of moles of butane? Again, we're only looking at butane right now, right? Because that's the molar enthalpy that we have in question. We have 2 moles of it, so I'm going to write 2 moles, right? for butane. I'm going to multiply it by our delta H comb. Delta H comb is this one. Well, I'm going to have to put moles on the bottom. I don't want the kilojoules to cancel out, because remember, when you have fractions, remember this is technically all over 1, right? If you have fractions and they're diagonal, they can cancel out. So I want them to cancel out because I do not want kilojoules to be canceled out. I want kilojoules to be left. Why? Delta H is change of energy. Energy is always measured in kilojoules, so this one has to be isolated on its own. I definitely do not want to cancel this out. So our moles and our moles will eventually cancel out. How many kilojoules? Negative 2,871. So we'll keep that there. So my delta H ends up becoming what? It becomes negative 5,742 kilojoules. Now where do I put this? This kilojoules I need to put on either this side or this side when I am dealing with the thermochemical equation. If I put it on this side, then it's going to be endothermic, which means it gained that energy. But we're dealing with an exothermic, so it has to be on the product side. It releases energy. So I just have to add my 5,742 kilojoules. If you're confused as to why it's a plus sign, it's because this is actually assumed to be negative here. Because it's on the exothermic side, it's released energy. I don't need to turn it into a negative already. I've already outlined it's negative here. But when you add it into your thermochemical equation, if it's on the exothermic side, the product side, it's assumed that this is negative. It released energy. If you've added this value over here, then it's assumed it's positive because you've taken energy. Now let's try another example. I want you to try it yourself. I have to write down the question, give it a try. So let's say the question asks to write the thermochem equation to represent, so I'll just put to represent dissolving 1 mole of AgNO3 silver nitrate in water in H2O. Also, delta H is going to equal 22.6 kilojoules per mole. Give it a try, pause the video. Okay, in order to solve this question, always write out our balanced chemical equation. Well, our AgNO3 over here. Ag is a solid, silver, so I'm just going to put a solid here. It's being dissolved with the water, so it's going to break up into its ions, the cation and the anion. So Ag is going to break up, has a positive charge. It's dissolved in water, so it's going to be aqueous. And then you add it with NO3, it's a -1 charge, and it's also going to be aqueous. We're done that. Don't need to really balance it out. It's already all balanced. Now we have to put my delta H, my enthalpy, on this side or on this side. This delta H is not that delta H. As you can see, it's per mole. So this here is not our delta H. So if I were to write out our formula again, so this is obviously not a combustion reaction, so I'm not going to put combustion, but the concept here is still the same. So our number of moles of our AgNO3 is what? It is just 1 mole. Right? You only see 1 mole over here, multiplied by 22.6 kilojoules per mole. Again, I want my kilojoules. I'm going to keep it on top. And I want my moles to cancel out. Right? So then this cancels out, this cancels out. So what do I end up getting? I end up just getting the same value, 22.6 kilojoules. Obviously, you could have done that in your head. I'm just trying to outline it here with writing to make it easier. So this 22.6 kilojoules, this is a positive value. It's quite obvious that this means it's endothermic. So which side is it going to be on? Is it going to be on this side or is it going to be on this side? It's obvious that it's going to be put on this side because it's absorbing energy. It's endothermic. I'm going to add it over here. That's it. Now our second methodology is going to be using a delta H value format. This is actually a lot easier for some students. Let's try off with a question. Sulfur dioxide and oxygen react to form sulfur trioxide. The molar enthalpy is negative 98.9 kilojoules per mole of SO2. What is the enthalpy change? All right, obviously have to put our balanced chemical equation. Let's get our sulfur dioxide. It's going to be gaseous. You add it with oxygen, obviously also gaseous, and sulfur trioxide, also gaseous. Now, let's balance it out. Pause the video, try to balance it yourself. Okay. We have 2 here, and we have 2 here. It's all balanced out. What is the enthalpy change? Well, we obviously have our formula. Is it going to be delta H comb or just delta H? This is a combustion reaction. Despite popular belief, it doesn't always have to yield CO2 and H2O. As long as it's an oxide, it's fine. It can still be a combustion reaction. That means we can actually put delta H comb over there. We're still dealing with a combustion reaction. Now, again, we're dealing with SO2, so let's solely fixate on SO2, and not this guy, but just this guy. So our delta H is equal to the number of moles of this guy. How many moles we have? We have 2. Multiplied by what? Delta H comb. So moles need to be on the bottom because I want my kilojoules on the top. And then I have negative 98.9. So this moles cancels out, this moles cancels out. So I'm left with just my energy, which is awesome. I'm going to figure out my enthalpy change. So negative 98.9 times 2 gives you a value, just let me use my calculator, negative 197.8 kilojoules. That's it. Now we're going to add it in a certain area. Are we going to add it here or are we going to add it here? Neither. This second model, all you need to do is write it on the side at the very end of the equation as delta H value, right, as shown here. And if it's a negative value, you just put negative. If it was a positive value here, you would just put positive. But because it's negative, we just keep it as negative. You're done. This is it. All right, try this one on your own, please. Write the thermochem equation to represent the exothermic reaction between xenon gas and fluorine gas to yield xenon tetrafluoride solid, given the reaction produces 251 kilojoules per mole of xenon reacted. Give this a try on your own. Alright, first thing we need to do, our xenon, it's gaseous, as stated in the question, added with our fluorine. Remember, fluorine, it is a diatomic molecule on its own, so please put a 2. and it's producing solid xenon tetrafluoride. Again, it has to be solid form, as stated in the question. Balance it out as appropriate. You get a 2 in front of that F2. Now what are we going to do? Well, we have to find out our delta H. So let's write our delta H is equal to our amount of moles multiplied by delta H. Is it going to be comb or combustion? Doesn't seem like it's going to be a combustion here. So I'm going to just put delta H. Okay, but the concept still remains the same. This is per mole of the compounds in question, or the element in question. In our case, it's the 251 kilojoules per mole of the xenon. That's the element in question. So that one needs to be looked at. We're xenon here. So our delta H is equal to our moles. So it's just 1 mole of xenon multiplied by delta H. It's written here. So again, I want my moles on the bottom and kilojoules on the top. Cancel them out, get the same value. All right. Question says it's to represent the exothermic reaction. Exothermic means it's a negative value. So do not forget to put the negative value there. So it's negative 251 kilojoules. Where am I going to put it? Don't have to stress much regarding reactant or product side. You just have to add it at the end. It's a negative value, so I'm just going to put negative 251 kilojoules. Just copy paste that, and then we're done. Now our third methodology is the standard molar enthalpy. Now what does that mean? The standard molar enthalpy, it takes into account the final and initial conditions. So let's look at initial, what happens. It first starts at standard atmospheric temperature and pressure. The pressure is going to be 100 kPa and the temperature is going to be 25 degrees Celsius. It's going to start at this condition, and eventually we need to measure an account of all the energy needed to get away from this condition. So the compound in question, get away from this condition. And then eventually, when all the energy is released, following the reaction, it's going to cool back down to SATP. Again, we're going to assume, sorry, I forgot to mention here, let's assume this is an exothermic reaction. Okay? So if it starts off and gets away from this condition and eventually it ends back, so it goes back to SATP, so that same condition here, this is represented as a standard molar enthalpy, the association of how much energy is required for that 1 mole of that substance. So if we look at a formula of carbon monoxide gas added with hydrogen gas, say this is gaseous, and methanol, and this is actually going to be a liquid. We can balance it out first, so now we're quite balanced. If the delta H for just 1 mole of this methanol that is being formed is negative 128.6 kilojoules per mole, this means that this CH3OH that has undergone the reaction and has formed, for every mole of this much energy was released. So I can actually put reacted to form as a delta HR for short. And this also must have undergone this condition from beginning to end, because this reaction here requires lots and lots of pressure, high amount of pressure, for these two to eventually collide and create methanol. But what conditions did we undergo? We underwent SATP in the beginning, and it went back to SATP in the end. So even if it's not a combustion reaction, because you can tell this is not combustion here, right? It's quite obvious. I can still get a value like this. And there's different types of these standard molar enthalpies, whether it's freezing, formation, even combustion. Okay? Why is this a little bit different than the combustion that we looked at? Because standard means that we have to put a not symbol up here. It means that any value that you're given, like this one here, for example, has undergone these conditions here from beginning to end. Hence why we put that symbol over there. So if we wanted to look specifically at H2, well, what would be the value or standard molar enthalpy of H2? Right now, this is only being related to the CH3OH. Well, if this is the value for CH3OH, and there's 2 moles of H2, if I wanted to look at just 1 mole of H2, so just per mole of H2, like I did here, well, this has a value of coefficient 1, and this has a value of coefficient 2. So if I just divide this by 2, then I end up just getting this value also just divided by 2. So that would just give you negative 64.3 kilojoules per mole. So for every mole of hydrogen, in order to create this, it would release this much energy. Lastly, our fourth methodology is going to be a PE diagram, or potential energy diagram. Now, with a potential energy diagram, as bonds break and reform, the positions of atoms alter. Therefore, changes occur in the potential energy. Okay? Now, potential energy, the best way to look at this is in terms of a diagram. Let's say potential energy is here on the side, and it's going to be measured in kilojoules. We always measure it in kilojoules. And then on the bottom here, on the x-axis, let's have reaction progress. Okay, so it's obviously increasing that way and increasing that way. Potential energy is equivalent to the heat transfer to or from the surroundings. So if energy is being transferred during such a change, this equals the change in potential energy as the bonds break or form. So let's have a look at a particular example here. Let's say we have a reactant over here, and it undergoes a change, so it releases energy, whether it's the help of a catalyst or it just broke apart. Regardless, it needs a certain amount of activation energy. Once it hits this threshold up here, it hits that threshold, it's able to undergo that change. So let's say it hit it. And now it released all that energy into its surroundings. So what's left of it? Not much. Not much is left. Okay, so this is now the product. So here is the reactant, and this here is the product. So what is the reactant going to be here? And what is the product going to be here? Well, let's just say that this was glucose, C6H12O6, and you add it with, let's say, oxygen. Okay, this is quite obvious. This is cellular respiration. So what is it going to produce? It's going to produce heat, but it's also going to be producing the products of CO2 and H2O. Now, we can also balance this out if you need, or if you wish. You can put a 6 over there, and a 6 over here, and a 6 over here. It's not the point of this illustration. The point is, there used to be a lot of potential energy here. but when it undergone that change and broke up and released all that energy outwards, there's not much energy left. So what does this mean? Well, a certain amount of energy was released. And that energy that was released, again represented as enthalpy change, the energy transfer, it only matters from the reactants to where the products are. So if I just find the difference between that, that's going to be our delta H. This is the amount of energy that was released. So this is our delta H value. For glucose, for every mole of glucose, the delta H is equal to 2,802.7 kilojoules. But remember, this is an exothermic reaction because it released energy. Via cellular respiration, the food that you eat reacting with the oxygen, it releases energy. So this value here actually has to be a negative value. So there's less energy at the very end in the products compared to how much there was before in the reactants. So this value over here can be a representation and is the fourth methodology of representing enthalpy through this PE diagram. So in order to summarize what we looked at today, we looked at our first methodology, which was our glucose. And we have to add it with this value here, because this 2,802.7 kilojoules is the amount of energy that was released. And in our first methodology, the thermochemistry equation, this value here, even though it's negative, if it's on the product side, it is going to be deemed as negative, even though we have a positive symbol here. Then we looked at the delta H value. So if we were to do it this way, you just put at the very end, our delta H is equal to our negative 2,802.7 kilojoules. Now our third methodology of the standard molar enthalpy, it's going to be delta H. I know it looks like it's combustion, right? It is combustion. However, we do have respiration. Again, this is cellular respiration, a special type of combustion, right, that happens within our cells. There is one for respiration, or resp. I'm just going to put a not over their symbol, and it's just this value over here that we found. Again, this is combustion, but there is a special one for respiration, so I'm just listing it here. It is negative 2,802.7 kilojoules. However, you do have to always remember, when we do standard molar enthalpy format, you have to also specify that it's per mole and the compound in question, or the element in question. So this would be C6H12O6. And then of course, for our fourth PE diagram, you can just draw it out this way and illustrate that this delta H is undergoing an exothermic reaction, because you see that the products are a lot lower than the reactants, and you list that the delta H here is represented by a number, is represented by a value. So this here is the fourth method.